Hello everyone. This is the second video on the network flow lecture. In the previous part, we have talked about the relation between maximum flow and minimum cut problems, that they are the dual of each other. And in this part, we are going to focus on the algorithm, how we can find a flow over a network with the maximum value. So the very first algorithm that might actually come to mind is that, okay, we are supposed to, in fact, assign some flows um, to all the edges, and this flow means that you are sending some material from the source to the target. So in fact, there should be some kind of path from the source to the target, right? So greedily, something that actually comes to mind first is that, okay, just find a path from the source to the target. We definitely need a path to be able to send some capacity, to send some flow. Find a path from the source to the target. Then, because the capacity of different edges are going to be different, you can just assign the maximum, you can assign a flow equal to the minimum capacity. It's like finding actually the bottleneck among all these edges in that path, and send um, that amount there, then try to actually find another path and equally just, just like the previous actually step, again through this path send the maximum flow that you can send through that path. So at first what we can do is that we assign the capacity of the flow of 0 to all the edges. It's just the initial flow to all the edges. At first it's going to be 0. If you wanted to send some flow, you should have a path from the source to the target, right? Find the path and find the bottleneck on that path and assign that flow to all of the edges in that path, and just repeat this procedure. Okay, this is going to actually give you a flow over the network at the end until you can't find any more path, but we are not sure if this is going to give us the maximum flow or not. And you probably have this sense so far that this algorithm might not really actually work and give you the optimal answer. But let's just apply it first over this example, and then we will go forward and see that how can we fix it. So at first the initial flow of all the edges are going to be 0. The capacity of each edge in this graph is clear, right? First of all, we can actually find a path, because we don't know that there might be actually different paths, but it is not really easy to say that which path we should take. So for now, let's just assume that I'm actually taking any path. So you actually take this path that actually has been shown in blue here, right, from the source to node 2, and from there to node 3, and from 3 into T. What is the minimum capacity among this path? It's going to be 10, and because we haven't actually assigned any other flow so far, we can say that, okay, we can send the complete amount, the 10 actually, into all these edges, right? So then the flow of this one is going to be 10, 10, and 10. So then look for another path, another possible path here, and send more flow if we can. If you look at here, you can see that there are some other actually paths from the source to the target, something like this one. But if you look at all of these actually paths, you can see that because I have already saturated this edge, it's not possible to send more flow through a path like this. There is another path, something like this one. Again, if you look at all the edges along this path, you can see that this one has been saturated and I cannot send more flow through this path. So it's just like this greedy strategy is going to give you this flow, and the maximum value of the flow is going to be 10. But is it the value of the flow is going to be 10. But is it going to be the maximum flow that you can find over this graph? The answer is no. The greedy actually algorithm here is going to fail, because we can actually find a better answer here. And what is that answer? So let me actually just show you what can be a better actually solution here. Okay, instead of actually sending the full 10 here, through the first path, instead of that, what you can actually do is that you can send the full 10 here, but what you can do is that you can send 4 of it here. Okay, because there is actually the capacity 4, and so far it's going to be 4. And then what you can do is that you can send another 4 here. And then you can send another 6 through this path. So, and the summation of all these is going to be 14 instead of 10, right? At the end, I have actually just fully used 10 here and 10 here. You can see that I sent 1, 4, and 1, 6, and 1, 4, and 1, 6, and I have used, in fact, 3 different paths to send all these 14 actually flow that from the source to the target. But the greedy version would just stuck, right? If you go with a path, take a path, because you don't know that which path, even if you actually just, for example, say that go find a path with the just like the shortest path or the fattest path. Find a path that has the maximum bottleneck or whatever like this. The greedy strategy is not going to find the optimal answer for you. If you stick with a specific actually path, take it, and you never actually change that decision, which is going to be greedy strategy, that's not going to give you the optimal answer. So now the question is how we can find the optimal answer. So in this kind of problems, in fact, the point is that you can actually make a decision, right? Go with a path, then later on notice that, okay, probably some part of it was wrong, right? I should do a kind of backtracking. So I find some answer in a couple of different steps, but then you actually need to, it's just like a search, right? I'm trying to say that we need to do a kind of exhaustive search again here to find the optimal answer. We need to search the space, the different possible flows that we can actually send to be able to find the optimal, the best actually flow, the flow with the maximum value. But this is going to be very complicated if you are actually doing the backtracking in this kind of problem, that how you are going to do the backtracking, how much you are going to actually just, are you going to remove the previous path that you take, or are you going to actually just reduce the amount of flow that you assign to that, for example, the previous decision, the previous path that you choose. It's going to be very complicated. The fact is, there is a very interesting actually algorithm for this problem that helps to model this kind of backtracking and find the optimal answer in a very smart approach. So before I can actually explain the algorithm properly, I need to define a concept which is, we call it actually a residual graph over your network flow, over your network flow graph. So what is a residual graph? Assume that I have a network flow graph. Okay, in my network flow graph, usually for all the edges, I'm going to have some capacity, right? And if we define some flow over this graph, it's supposed to actually have some flow and some capacities, two different actually values for the same edge, right? That one value shows your capacity of the edge and one value shows the flow that you have already sent. Okay, you have already assigned this much actually flow to this edge. Both of them are assigned to the one edge. So the residual graph is telling you that instead of actually working on your graph with just for each of the edges, you just have one edge and keep two different values. Instead of keeping two separate values over the same edge, create two edges, and for each one, assign actually one of these one value. So instead of having just a V and W and one edge between them, maybe in your original graph you have actually another edge here. I'm not talking about that, okay? So it just basically tells you that if you have an edge, let me just remove this one, from V to W in the original graph, instead of that edge, what you can do is that you can have a reverse edge from W to V and change the values that you assign to these edges. The flow that you sent in your original graph to this edge, you can assign it, it's going to be 6, you can assign it to as the capacity of the residual edge. And this is going to actually give you the residual graph. One thing or more that you are going to actually change is that because your previous actually capacity, the original capacity was 17, if you are passing any amount of flow through this edge, it's just like you are not able to actually pass more than 11 flow over this edge after this, right? So the residual capacity that you define in your residual graph is going to be, for the original edge, is going to be 11. So it's just telling you that instead of just having one edge here from V to W, define two edges, one of them from V to W, that actually the number assigned to that is going to be the maximum capacity minus the flow that you have already assigned, and the residual capacity of the edge that you are adding from W to V is going to be equal to the flow. Okay, so in this way, if you do this, you are going to have a new graph that's going to be called the residual graph. You might ask that, what if there was already an edge from W to V? There might be an edge in the original graph as well, right? So what would happen in that case is that, for example, if there is an edge from W to V, what you can do is that you can actually, in fact, add the flow that you have here to the capacity of this edge. So if in that case is supposed to be some capacity for this edge, right? Some capacity. What I'm writing here. Whatever is the capacity of this edge, just add that flow to this capacity. And if you already actually sent some flow here, just add that flow into the residual capacity of the from V to W. So don't be confused. It is, yes, it is possible to have both of these two edges. You can just add both flows there. So now if I go back to my previous example, after this was the original actually graph. After I found one path here, it was the path, right? And I assigned the bottleneck of this path is 10, and I assigned 10 flow over all of these edges. Okay, and the rest of the flows were 0. And I also have the capacity for all of this. So this is the original graph. I can create a residual graph corresponding to this. So in the residual graph, what would happen is that because I have already fully used the flow here, what would happen is that it's just like I am adding an edge here in the residual edge. The capacity of the residual edge is going to be 10 here. These previous arrows was just showing you the path, not the edge. I need to actually add another residual edge here with the capacity 10, a residual edge here with the capacity 10. Okay, what would happen to the original edges? For the original edges, it's just like this edge is going to go with the capacity 0, this one is going to go with the residual capacity 0, and this one is going to go with the residual capacity 3. Because these two are zeros, it's just like you don't have an edge there. Because if it is 0, it's just like you can't actually really pass anything through 0, right? That's why in this graph that you can see, I didn't actually show those edges with the residual capacity 0. I don't show them in the graph, but you can actually assume that yes, there is an edge there with the residual capacity 0. But anyway, if the residual capacity is 0, you cannot send anything through that edge, right? So keep that in mind. Okay, so this is our residual graph after finding the very first path. That first path that we actually sent out something. Let me actually use a different color. This was the very first path that you find. After finding that path and assigning the flows, create the residual graph. Now the trick here is that instead of looking for another path in the original graph, look for a path in the residual graph. Okay, so it's just like after I found one path, now in the residual graph still I can look for more paths. Why it is possible? Because I have some edges added here, right? And look at this part. Now you can see that what I can do is that I can find a path from S to T through this path, right? It might look actually very complicated to you, but in the residual graph, what does actually, in fact, this one tells me? This one tells me that you can send 4 flow, whatever flow. Let's just not talking about the capacity. You can send some flow from this node to this node, and from this to 3, and from 3 to 2, and from 2 to 5 and from 5 to t. Maybe you say that this is not such a, there is no such a path in the original graph. That's right. What's happening here is basically exactly the backtracking that I am looking for. It is telling me that don't use the full 10 capacity here. Remember in the original graph, in that greedy algorithm that we talked, what we did was finding a path from S to T, right? And assigning the maximum, assigning the flow to be the minimum capacity among all of the edges, which was 10. So because I fully used 10 here, here, and here in this edge, I couldn't use another paths to find more, right? So the wrong, actually the thing that was wrong in the previous in the previous steps that I took was that I fully used this path. I sent 10 through this path and I couldn't actually just redo it. But now using the residual graph, I can redo some part of actually that flow that I sent through this path. How much of it will be actually redo? This is exactly this 4. If you assign 4 here, 4 here, 4 here, and 4 here, what would happen is that you would actually send 4 flow, and if you are sending some flow over this residual path, it's just like you are redoing some part of the flow from the previous path. So now the residual graph would look like this is going to be 6, and this is going to be 7. Right? And then it allows me to find another path, yet there is another path here. You can actually, so here it is, you are going to actually have a residual path here. Let me actually just show it to you in a different graph. It just became too messy here. Okay, in fact, this one, in this residual graph, I still look for another path. Let's just see that this is going to be actually that path that I showed you. You find this path, this blue path, and then you would create the residual graph now, and now you can see that you actually continue finding these paths that you call them the augmenting path, and whenever you cannot find any more path from the source to the target, you can actually make sure that it's not possible to send any more flow through this graph. And this is exactly that step, that I cannot send any more flow. The fact is that you can see there is no more outgoing edge from S, so that it's not possible to send more flow. So whenever you reach to this point, you say that it is going to be actually the maximum flow that I can send. And from the residual graph, you can actually simply find out what is going to be this is the residual graph, right? From the residual graph, you can find out what is going to be the flow of each edge. So in fact, in the original graph, the flow here is going to be 4, here 10, 4 of it will be passed here, 6 here, 4, 4, and 10. Okay, it was different than the original actually solution that I showed you, but the answer is the same. The maximum flow is 14, the same as the one that I showed you. Okay, this algorithm is called Ford-Falkerson algorithm, that we can prove that this is going to give us the optimal answer. I mean, the idea was brilliant. How they, in fact, tried to implement backtracking, but not really using the usual actually way of backtracking and redoing a decision.